we carry out how do we measure this property. In order to measure this property, we use a tensile testing system, okay, in a machine which is known as actually universal testing machine, in which we find out properties like for example, ultimate tensile strength, yield strength, okay, percentage elongation, Young's modulus of elasticity, etc. Okay. So, I have just now shown you that in a UTM machine how we are we can deform the rubber specimen, the same specimen that I have shown you, okay, can be used in this case. Universal testing machine is a beautiful machine where you can actually load a sample in various ways, tension, compression, shear. Not only that, the loading can be made dynamic loading and which can include things like fatigue, etc. So, that is how do we generally carry out this universal testing machine, the tensile testing. Okay. Now, if you carry out such testing of a ductile metal, okay, how would you find out the stress strain diagram, and that is the the engineering stress strain diagram of the material. How do you usually see the stress strain diagram? If you look at it, that the stress strain diagram shows certain features, but please keep in mind that this is for a ductile metal. Okay. So, you will see that there is an initial region where the material, if you actually unload the material, it will come back to the same point itself, and that is known as the elastic limit. Okay. That means the maximum stress that it can withstand without any measurable permanent strain after unloading. Now, in the elastic limit, of course, there are two regions. In one region, up to some region, it is actually perfectly linear, and beyond that it is slightly nonlinear, but still if you release in the nonlinear region, it will come back to its original position. That is what is the defines the elastic limit. Now, then the point comes here, that is the yield strength point. Beyond the yield strength point, if you actually deform the material, then it will start to deform plastically. So, what it means is that beyond that point, if you actually start to unload, there will be some amount of deformation which will always remain into the system, and that is why the yield strength position is very important, because that says the onslaught of actually plastic deformation in the system. Okay. So, as I am increasing the load, I am going beyond the yield strength level, and I am actually watching the uniform plastic deformation. Now, if I increase the load further, what is going to happen is something like a necking phenomena that would start to happen, okay, and then the material will go to the fracture. Okay. So, that is what generally happens for a ductile material. So, in that, beyond that necking point, what you get is a non-uniform plastic deformation. So, the plastic strain itself can be divided into two parts. One is the when it is uniform plastic deformation, okay, that is the first part, and then when there is a non-uniform plastic deformation till failure. Okay. So, that is what we will find into the system. And what is the point that is important for us is that up to the necking, we get actually the ultimate tensile strength. So, that is the maximum load divided by the original cross sectional area of the system, that gives us the ultimate tensile strength. Okay. Beyond that, you would not expect a strength of the material, because beyond that, if you take the force, it is actually going to take us towards a fracture. That is why ultimate tensile strength plays a very important role in terms of the product design. And also the other two important factor is that what is the percentage elongation, that is the ratio of the difference of final to initial length change over the initial length, and similarly for the area. So, that actually tells us that how compliant is the material. So, this is a typical stress strain curve for a ductile material. How will it look like for a brittle material? Okay, I can just in a very small qualitative manner we can draw it here, that suppose the stress is denoted by sigma and strain by epsilon. So, if I draw the sigma epsilon for a brittle material, it is just one single line, okay, and maybe some point of nonlinearity, but that is it, and then it sharply fails. That means, it will not show any plastic strain, any plastic deformation. Okay? That is generally happens in terms of the brittle material. The other important point here is that generally the yield strength, if you do not find a very sharp point where this this is happening, we consider approximately this 0.002 level, that means the 2% strain level. We find out that where it is intersecting, and that point is defined as the yield strength level, because that is generally the strain level which it can take in general in metals without any permanent deformation. But this is very specific to the metals. For the things like elastomers or rubbers, this can become something like 5% to 10%. Okay? So, depending on the material, this position. So, that is about the stress strain relationship. There are some other mechanical properties which are also important. One of them is ductility. I already talked about it, that it is the how much is the capacity of how much you can draw a material under the tensile stress, okay, and that is very important. And there is something that you will also see in terms of ductility, which is known as the ductile failure, the telltale sign of the neck formation of the system, and the brittleness of a system. So, the difference between a brittle and a ductile system, I have already drawn the stress strain curve for a brittle system, and a ductile system is that precisely this ray, the presence of this plastic strain, that is there for a ductile material, and that is absent for a brittle material. So, that is very important point that we have to keep in our mind while comparing between various material properties. Now, the other important point here is actually the resilience of a material, which is the capacity of a material to absorb the energy, okay, elastically. So, it is in the elastic domain. When it is deformed elastically, how much of energy you can absorb, and if you consider the stress strain diagram, and if you consider the area under the stress strain diagram, you can actually find out that this is something like sigma y square over 2e in a kind of an approximate measure, and that is, so that means if you know what is the yield stress and if you know what is the modulus of elasticity, you can actually compute that what is the resilience of the material in terms of modulus of resilience and how much of energy the material can absorb, which is very important in applications like spring type of applications. So, the resilience is another important mechanical property. The last important property in this direction is the toughness. Toughness is also the area under the stress strain curve, just like the earlier case, but here you are considering the plastic region also. Okay. So, earlier you are confining yourself within the elastic region, now you are considering the plastic region also. In fact, the test that is very much important towards this direction are actually IITB and Charpy impact test. So, this is an IITB impact test, where actually you support the sample from one position here, you are supporting the sample and you are hitting it through a pendulum, and if there is no sample, then it can go to a particular distance. If there is a sample there, then some energy is actually taken by it, so it cannot go up to that distance. So, you take that ratio of the two, the return ratio we call it, and then that gives a measure of how much of energy is actually absorbed by the material, and which is a measure of the toughness of the material. Now, similarly, there is another very similar test actually, which is known as the Charpy test. Now, the difference between the two tests, the IITB test and the Charpy test, is that in the IITB test you have for example, if I go to the last case, you have the crack, which is you make a notch actually, and the notch actually faces the hammer. So, the hammer faces the notch, So, you are in terms of Charpy, as you can see, on the other hand, the notch is at the opposite side of the hammer. So, that is one of the difference between the two, and also in case of a Charpy test, you are supporting the material at two places instead of at one location. But both of them are very good tests which can measure that how much of energy a material can absorb, and that means how tough the material is, and that actually means that how much is the impact strength that is there in the material. So, here is some kind of a comparison of a from the Ashby's table, and as you can see here, if you look at it very closely, that the metals are topping in the list actually, because they can absorb quite a good amount of impact energy, and in fact plastics, even though they deform more, they cannot absorb that much of energy. Brittle materials of course are the worst here. So, that is what is in terms of the three different groups of materials, and composites are somewhere in between. Now, the factors that are important in terms of the impact energy is that for a given material, the impact energy will decrease if the yield strength is increased. So, that is generally found in a material, and the notch serves as a stress concentration zone. So, some materials are more sensitive to notches, and the most of the impact energy is actually absorbed during the plastic deformation of the material. Also, temperature and ductility plays a very important role on it. So, this is where we are going to close this lecture, and in the next lecture we will talk about a few more mechanical properties, that is the hardness of the system, the creep of the system, and the damping.